Louis, and it's a very pleasure to be here in Austin. This is my first visit to Austin. How many years have you been here?
7 years, maybe?
7 years, yeah. I've been always trying to come to visit you, and it's very great to have this opportunity. So, I think robotics is really undergoing a great transformation, and I mean, the idea of robot has been around for many years. And as you know, the first robot, the Humanoid, was deployed in 1961, and that was sort of the mark of the beginning of robotics. And since then, we have millions of robots all around the world. These are members from IFR, the International Federation of Robotics, and this doesn't count all the service robots, all the other robots that are not really in manufacturing. So, in recent years, in the last probably 15 years, we started to see an increase of robotics in many domains. Medical robotics is a very successful area of robotics that is bringing this technology to surgery, to many aspects of healthcare, and in fact, it's quite successful today. There are a increased number of companies in everywhere, and there is a lot of extension of this to think about distant medicine that can reach villages through those technologies, and that can connect people to cities and hospitals. Social robotics is also a growing area, and we have seen an increase in interest in social robotics, actually in deployment of social robots. And there are conferences now, there are journals publishing work, and this is an area that is really interesting because it brings engineers, researchers, scientists, and social scientists, and brings a number of people together to think about those aspects of robotics. We have all kinds of technologies that are bringing more and more interaction with virtual worlds, with physical environment. We have a lot of augmentation of human that is taking place through all kinds of devices that are coming from several aspects of robotics, exoskeletal systems, sensors, and control architectures. Service robotics is growing, and we see a lot of development in those areas, and there is much more that is coming at the frontier of robotics that still is not mature. We talk about the domestic robotics. Well, if we look at this picture, we see a robot and a human, but there is maybe a sort of cognitive interaction with little physical interaction, where the robot is really making the coffee or the tea. And this goes back a little bit to what you were saying. I mean, there is the image that there are high expectations without really realizing that, yes, we have this image, but do we really have cooperative robots working today? And this is going to be amazing. We are going to transform the assembly line that is very costly, that was the technology that was used when we introduced robots in industry and automation into a collaborative work between human and robots. And the reason is assembly lines are very costly, are probably the most costly part of automation or the product that we are building. And when we want to modify the design, it's very difficult. When we want to take this to a small industry or mid-sized industry, it's very costly, so we have little automation in there. So bringing this connection between machines and human could be really amazing in terms of bringing new capabilities to small companies, to changing designs, and to a low-cost products. Not only we are talking about this in the context of manufacturing, but also in many other contexts where now not only we have manipulators, but we have mobile manipulator structures that are distributed and moving and performing all kinds of tasks. These are still concepts and in the research at KUKA and others, but this is the direction we see robotics going into. So these are still maybe indoor capabilities, but if we think about going further to where really robotic would be amazing, is to take robotics where human cannot go. But still we need to reconnect the human somehow. So if we want to send a robot in a mine, then probably we are not going to be able to do it because we don't have that autonomy today. But we can imagine reconnecting the human brain and embodiment to the machine and creating a system that can work. So I'm going to start by talking about La Lune, an experiment that we have been pursuing at Stanford and in collaboration with our colleagues in Drassen in France. La Lune is a vessel of Louis XIV from the 17th century. It is an example of many shipwrecks that are in the Mediterranean and all around the world. It sunk in 1664. Well, the challenge to reach a shipwreck like this is the fact that it is at 100 meters, beyond where divers can go. Any diver here? No divers? All right, well, divers maybe comfortably can go to 40 meters, maybe a little more, but then there are ways of doing it, and they are very challenging. But let me show you how we reach 100 meters. So,
do we have the microphone?
Oh, no, it's le son public.
Super especializados. São especializados em robôs, não são especializados em PowerPoint.
Yeah, okay, we will try again then. Thank you. So the way we can do it is by basically bringing the diver inside a suit, and inside the suit now you are going to be in an environment that is pressurized, and the diver can go there. However, the diver is stuck inside this very rigid, bulky, very difficult to move suit, and the human is not going to be able to do anything except the fact that he's there and can move the arms to grasp objects and move objects. So this is for 40 meters, and we really have to do a lot of maintenance. I mean, all the accidents in the Gulf of Mexico. If we think about the accident in many places around the world, when we think about all the work that is needed and how difficult it is. And to illustrate that, let me show you a short video.
C'est le plus récent et le plus sophistiqué des bâtiments de soutien à la plongée.
C'est en français. So this is a task at 150 meters. 150 meters, you cannot go without really special treatment. So you have to stay 1 week inside a container they provide oxygen with helium. And now you are conditioned after 1 week, then you can go that deep to 130 meters. And after after like few days of work, you go back and you need another week to be reconditioned. So working at the depth of even 130 meters is impossible. I mean, and very dangerous. And anything that can happen in the water makes it really, really dangerous, because we cannot bring the person outside or bring anyone inside. This is a completely crazy situation, and those people are just so brave to do that work. And we are talking here about 150. So, what is the reason? Why we cannot have robots that can do that? Well, most of robotics today, especially underwater robotics, is amazing vehicles that those vehicles can only see. They cannot do. So when they have arms, they are very rigid, and they need to be teleoperated, and they are very difficult to interact with the environment to do real tasks. So the project of Ocean One that we launched at Stanford aimed at building capabilities of bimanual manipulation together with the mobility of the robot was completely aimed at creating a virtual diver. A diver that can dive for the human, but in a way where the human is reconnected with the machine. So the reconnection is done through a haptic interaction. So this is a haptic device controlling a robot. When the robot is going to move, it's moving to make contact, the human is touching and feeling that contact. So in here, the human is going to feel what the robot is touching when the robot is reaching the bottom of the ocean. So in a way, we are reconnecting the human with the machine. And in this concept, we are also thinking about the power. Batteries are not yet that powerful to provide enough time for all operation. So there is a relay, and that provides the power. There is communication issues where we need to deal with the fact that acoustic is slow, so we need to use optical modems to create fast communication that allow the human to interact with the machine. So building a machine like this, I don't know if you tried to build a robot in your lab. I know you did, some of you did, but it is really hard. I mean, in a laboratory with your students putting together a robot, we had a lot of support from Mecha Robotics, and our students were really, really hard. I mean, designing and developing and building this robot, and finally assembling the robot and putting it all together. Now, once you build a robot like this, you need still to test it. This robot is 200 kilograms. You cannot test it in the lab. It's like in space. In space, most of those robots are too heavy in the air. So first we simulate the robot. So haptically we are interacting now with the simulation. And the simulation was amazing because it brought a lot of issues about how to design the robot properly and how to create those capabilities on the robot, and what type of sensors and what type of actuators we needed. And then you finish the robot, you take the robot, you push it all the way to the pool. So you need a slope to take it. It's 200 kilograms, really heavy. And then you discover there is a problem. So you have to take it back and forth, and finally you see the robot growing and becoming more and more autonomous. The robot here is playing the dolphin, quite happy, and the question in our discussion about La Lune is, well, we want to manipulate fragile objects with a robot that is capable of reaching and grasping those objects and removing them while under interaction with the human expert. Well, this is not the only area applications. Obviously, we have all the work that we need to do for the environment in the water. We have coral reefs, we need to place sensors, we need to collect samples, we need to do a lot of work at that. We need to do maintenance, as I said and discussed earlier, where we have so many offshore platforms, structures underwater, and potential resources underwater. 70% of the planet is covered by water. We can go to 40 meters, which is really a whole world to discover and to explore. But all of this is just an example of what we want to do with robotics in the field. That is, think about all these high altitude stations where we cannot place human to operate. And can we now substitute for human there with machines that are connected to the expert that can operate those machines? Mining. Well, mining is really one of the most dangerous and expensive. I mean, we are bringing people to 3,000 meters, putting oxygen and cooling and all those conditions. I mean, when we know that in space as well, when we need to place a human, it's much more costly in those environments. But obviously, we cannot have a robotic system that can operate and perform underground on its own completely. However, we can imagine again a robot that can make use of the same tool that the human is using, and then connecting the human from an interface to those robots. Well, the thing we see today in robotics is huge progress, but most of this progress has been done in mobility. We somehow avoided the hard task of dealing with manipulation. And I mean, frankly speaking, I observed this from the 90s. We go to an ICRA or IOS conference and we see sessions and tracks all through the conference. Mobile Robot 1, Mobile Robot 2, Mobile Robot 3, and Navigation 1, Navigation 2, and all of that. So we really have to just go beyond this. I mean, when we talk about Pepper and think this is a robot, well, it is a mobile platform with some way of communication. And unless we really move towards robots that are capable of physical interaction, we are really not really dealing with the problem fully. Here is an example. If we think about Ashimo, it is an amazing machine that really perform and show capabilities of running and jumping and doing all of those things. But when it comes to doing manipulation, by the way, Ashimo came to Stanford for about 10 years, enrolled in a master's program and learned how to perform physical interaction, and graduated and returned back to Japan. The reason is, in a task like this, Honda, in order to demonstrate the potential capability of a robot, will have to go through a lot of incredibly complex programming for this specific task. And the reason is we go and program robots still at the lowest level of joint motion, coordination, to create that kind of behavior. Well, this was okay when we were in industrial robotics, doing over and over the same thing. But this is not going to work anymore when we go to unstructured robotics. And besides, how come a little child is able to do it? What is the secret? I mean, how come human do it so easy? So when we have over and over the same task, yes, we can invest and put our robot to extensive detailed programming and place fixtures, organize everything, jigs, and all of that to create a pre-programmed robot. In those environments, when we are going to interact between those robots and the human, we really need capability that is generated in real time. And the only way this can be done is by lifting the level of programming of the robot to much higher level. We need more abstraction. We need to deal with this in ways we're talking with the robot at the level of the task. We need to build manipulation skills. Humans are amazing at their abilities to build skills and develop those skills very quickly. They learn them and they develop them. And the question is, can we learn something from humans? It turned out one of the key aspects of all these skills, if we think about them, is that, first of all, we don't care about trajectory. We don't care about the actual position. What we care about is the way we feel the contact and understand the geometry and move between these different objects. So compliant motion is key in many aspects of human strategies. And here is an example putting face-to-face two objects where the contact information is guiding the motion. Once we have that, we can transform the problem. Contact is maintained as objects are moving. The environment is moving or changing, and the robot is capable of maintaining the contact. This is building a strategy that is independent of where things are happening, and this relies on this information about contact. So we need to perceive, we need to touch, feel, and then understand the geometry and resolve that information as a strategy for the robot. So how can we do it? Well, we can go and study human motion. We can look at a human performing this task from many different initial conditions and try to find what is going on and what is the strategy. Very often in learning, what we do is we say, well, we have those trajectories and we try to rebuild another trajectory when we encounter a situation like this. This is going to be very limited to some geometries, to some examples that we encounter. And this is not the point. The point is, can we extract the strategy behind the motion? Can we find something yet higher level of abstraction with respect to this strategy? And this is what we are after. And once we do that, the robot is going to be able to perform this task for different geometries, feel its way, that means sense the environment that is changing, and detect and be able to move even despite errors in grasping, or even if the robot is being pushed around, and this is due to the way we separate the task and the posture and the different aspects of the control of the robot. Now then we can go and generalize and think about those tasks which are not easy, even human, if you are not paying attention. Putting just two objects together is not that simple. Well, once we have that strategy, the robot is going to be able to perform this. In fact, here is an example of a piece that is going to be placed on the wing of 787. And the program is the same. We keep disturbing the program, and the robot is using those strategies, searching, finding the features, and doing the compliant motions, is able to do over and over this. Every time we disturb the robot finds its way and goes back. Come on, do it. Yes? Yes. All right. So, another problem, in fact, Lewis worked on is the multi-contact. I mean, it's already very hard to do one foreign contact and create compliance, but what about when you have multiple of them? How do you deal with the multi-contact, which is part of everything? If I'm reaching for something, I have contact with the body, I'm going to brace, and I'm going to reach. In all these situations, you have multi-contact beside your contact with the ground. So, building capabilities for multi-contact and really understanding all the aspects of this requires not only dealing with the contact and the multi-contact themselves, but also the internal forces created as we perform those contacts. So a humanoid robot is going to require not only to control the task, not only to control the posture, not only to control the constraints, not only to control the balance and the contact and all these different things. And this brings about a lot of things. And if we go and take this and represent it in configuration space and put the goal in configuration space, good luck finding the solution in real time. So the question is, how human do it? And it seems like all the time we go back to the human. Please tell us, how do you do it? And then we come back with answers. So, well, human, and we don't have too much time to do the experiment, but we can all of us see the intuition. We focus on the task, and we move toward reaching for an object, but then as we start reaching, the body says, oh, the shoulder is going to be far away and we cannot move, then the posture is going to be adjusted and the shoulder and the body will move. And there are sort of like separate controllers taking place, handling the task, the posture, and all these different things. And that results into a sort of representation in our brain about how we are performing or about to perform a task, and how we are doing the motor control of our muscles to do all that coordination. And we have done a lot of studies in that area that actually is showing that there are this separation. There are separate controls that are taking place, and they correspond to different representations. So I'm not going to try to go deeper in this because it will involve a lot of technical development. But let me just say, when we start the problem, we define a task. We have to do the balance. We have to deal with the constraints, all these things that are there. And then we have to control the contact, the multi-contact. We have to control